Hey everybody, we're live and in stereo. I've started the recording and let's just finish what we have started and let's just put an end to Hess cycle and all of the extra stuff that we need to know. And before I teach you guys what's remaining of the Hess cycle, in the last 3-4 classes, we've done a lot of practice, more than which is required for our exams. But now when you look at the exams question, they'll seem like a piece of cake for you because your concepts are crystal clear. You know what enthalpy change of formation is, combustion is, neutralization, solution, all of that good stuff is known to you guys now, right? So we've done it, and we've done so many examples in the live class that they cover almost all the past paper questions, all of them in the last 2-3 classes, right? And along with all the definitions. Done. So today, I'm going to teach you the last bit, the last link of Hess cycle, which is with O-levels and IGCSE. And I obviously don't trust whoever you've learned O-level IGCSE from, so I have to give you guys a quick recap of what you've learned in O-level and IGCSE before linking it to Hess cycle, right? Now, what was the idea in O-level and IGCSE, which we had learned about something known as bond breaking and bond formation, right? What was that idea? Anybody remembers? If you guys remember, you know that bond breaking in O-levels and IGCSE, you guys had studied that bond breaking is what? It's a what process? Bond breaking is an endothermic process, right? And bond formation is an exothermic process. I think this should be on our fingertips now, right? We've also covered it in AS level, but bond breaking is an endothermic process and bond formation is an exothermic process, right? And if I focus a little on bond breaking, you need to now also understand what exactly do we mean by bond breaking is an endothermic process. In O-level IGCSE, you just used to rote learn this, right? Bond breaking is endothermic, bond breaking is endothermic, like a parrot. You never really knew what you meant by bond breaking is endothermic. Please understand that whenever heat is taken in from the surroundings, right, it's an endothermic process. And to break a bond, if you have a hydrogen bonded to another hydrogen atom, to break this particular bond right here, you need to take in heat energy from the surroundings. So effectively, heat energy or thermal energy is taken in during bond breaking. And we know that whenever thermal energy or heat energy is taken in or absorbed, what happens? That's an endothermic process, and that is the reason why bond breaking is endothermic. Why is bond breaking endothermic, sir? Sir, bond breaking is endothermic because heat energy is taken in from the surroundings. Thermal energy is absorbed from the surroundings, and that's what leads to bond breaking being endothermic, because in order to break a bond, you need to take in the heat energy from the surroundings. The question is why, right? That should be a question in everybody's teeny tiny brain. Why do you need to take in heat energy to break a bond, right? Muhammad, we've already done all of those examples of combustion and all formation. If this is your first class, then you've missed out on all of those classes. It'll be uploaded onto YouTube. You can check them out by searching on YouTube, the page at Carbox Hilchem. You'll find them there. We've already done everything. This is just a wrap-up class, right? Okay. So the question is, why do we need to take in heat energy to break a particular bond? The idea is that whenever, and I'll show you guys a diagram, that'll help you understand the idea much better. That'll help you guys understand the reason why energy must be taken in to break a particular bond, right? So give me a moment. Let me add a picture to show you guys what exactly happens when a bond is broken, right? And this is all conceptual clarity that needs to be in your brainerinos. One of the videos have been uploaded, Mohammed. The other one will be uploaded tonight, right? See, this is the reason. This diagram is the reason why heat energy is taken in to break a bond. Because understand that whenever you need to break a bond, you need to overcome or break the attractive forces between the shared pair of electrons and its nuclei, right? So you understand that if a hydrogen atom is bonded to another hydrogen atom, there are attractive forces. This nuclei is pulling these shared pair of electrons. This nuclei is pulling these shared pair of electrons. And that is why this is a strong covalent bond, right? And if you were to break this bond, you need to take in the heat energy. Why do you need to do that? You need to do that to overcome the attractive forces. Here you have attractive forces, sir. So in order to break a bond, you just need to overcome these attractive forces right here. And that is the reason why heat energy or thermal energy is taken in, right? Why? To overcome the attractive forces between what and what? Between shared pair of electrons and its nuclei. Shared pair of electrons and the nuclei. And I think it's also written in the diagram. I hope it's written. See, you have to effectively do work against it, right? See, you need to pull these atoms apart, right? And in order to pull these atoms apart against the force of attraction, right here, you need to take in heat energy. See, to break a covalent bond, the attractive forces between the shared pair or pairs of electrons and the nuclei of the two atoms need to be overcome, right? So that's the basic idea of why bond breaking is an endothermic process, because you need to take in the heat energy to break the attractive forces between the shared pair of electrons between two atoms and its nuclei, right? That's the reason. Okay. Now, this heat energy that is taken in, this heat energy which is taken in to break this particular bond, this heat energy is effectively called bond enthalpy. Right? In simple terms, bond enthalpy is basically the heat energy which is taken in to overcome the attractive forces between a shared pair of electrons and its nuclei, right? Or it's also known as bond energy. But the better term for it in AS level would be bond enthalpy. But if I were to properly define bond enthalpy, and you need to know this, if you were to properly define bond enthalpy, you would define it like this. Hey, you will be like, hey, bond enthalpy is basically the amount of energy required, right? We need to provide energy. Why? It needs to, we need to take in heat energy right here. Why? To overcome the attractive forces, right? So it's the amount of energy required, and because it is the amount of energy required, it's always required. That's the reason why bond enthalpies are by nature endothermic, right? Bond enthalpies by nature are endothermic. Okay? So it's the amount of energy required to break what? To break bonds, right? To break, but which type of bond? So to break 1 mole of bonds. Which bonds? 1 mole of covalent bonds. To break 1 mole of covalent bonds. But which bond are we talking about? Which 1 mole of covalent bond? Sir, 1 mole of a specific covalent bond. Specific. Are you talking about hydrogen's bond? Are you talking about chlorine's covalent bond, ClCl? Are you talking about N2's bond? Which bond are you talking about? So to break 1 mole of a specific covalent bond between what? Between two atoms. In 1 mole, and I'll explain this definition to you in a moment with more clarity. In 1 mole of gaseous molecules. In 1 mole of gaseous molecules under standard conditions. You could write this under standard conditions, like we have been writing, right? We know what standard conditions are, right? 298 Kelvin and whatever. BS, right? Now, what do we mean by this? The amount of energy required. We know that we need to provide energy to break a particular bond. And so bond breaking is an endothermic process, right? So that's that idea we already know. But what do we mean by 1 mole of a specific covalent bond? Why 1 mole? Please understand that in labs, when we talk about hydrogen bonded to a hydrogen, we don't talk about a single molecule. We never define things from the perspective of a single molecule, because a single molecule, playing around in the laboratories, in the chemistry laboratories with a single molecule is near to impossible for our school labs. We can't do that stuff. We need to talk in terms of a particular number which we can actually utilize. And that number we've already studied in moles and stoichiometry is a single mole. Because we can properly play around with 1 mole of molecules, right? A single molecule is very, very tiny. I can't even do anything with it. So why would I define things by just saying a single molecule to break a covalent bond of a single molecule? No, I want to break covalent bonds of 1 mole of these molecules, right? And that's why we say we need to break 1 mole of specific covalent bonds, which is effectively 6.022 into 10 to the power 23 covalent bonds which you need to break, right? And between two atoms in 1 mole of gaseous molecule. And this is what is so important. Please understand that whenever we talk about bond enthalpies, we assume the idea that all of these elements or molecules that I have, they are gaseous. So hydrogen gas, chlorine gas. If I were to break the bond, they should be in its gaseous state. Bond enthalpy is defined from this perspective, right? So O2 gas. They should all be in its gaseous state, and after I break the bond, I'm going to end up with 2H gases. After I break the bond, between Cl and Cl, after I break this fella right here, I'm going to get 2 Cl gaseous atoms. After I break the O double bonded to O, I'm going to get what? I'm going to get 2 O gaseous atoms. And this is effectively what bond enthalpy is. And it makes sense. It even makes sense. If you have 1 mole of gaseous molecules, you will have 1 mole of covalent bonds, wouldn't you? If you have 1 mole of gaseous molecules, you're going to have 1 mole of covalent bond. 1 mole means how many gaseous molecules? It means 6.022 into 10 to the power 23. If I say, hey, you have 1 mole of hydrogen molecules, you have these many H's, right? And so you'll have these many H bonds, H bonded to H. And that's the reason why I'm saying to break 1 mole of specific covalent bonds between two atoms in 1 mole of gaseous molecules, right? So that's the idea of bond enthalpy, and we've already studied this. And it's also worth noting that although bond enthalpy is defined from the perspective of endothermic process, you also know that if I say, hey, hydrogen gas, if I were to break the bond between two hydrogen atoms and end up with 2 hydrogen gaseous atoms right here, if I were to break the bond right here between H and H in a molecule, 2 hydrogen atoms in a molecule, and I end up with 2 hydrogen gaseous atoms, this bond enthalpy, let's suppose I say, is plus 436 kilojoule per mole, right? Because remember, bond enthalpy is for 1 mole of gaseous molecules. So if I were to break 1 mole of a specific covalent bond in 1 mole of gaseous molecules for hydrogen, I'm going to end up with this much energy, right? And it's also worth noting that that if I were to go the reverse way, if I were to form a bond, bond formation, if that were to take place, what would happen? Bond formation is exothermic. So the same magnitude of energy would then be released. So if I were to form a bond between 2 hydrogen gaseous atoms and form H2, right here, the energy that would be given out would be the same in magnitude. This is plus 436, and then that would be minus 436 kilojoule per mole. So the magnitude would be same, but the sign is different because bond formation is exothermic and bond breaking, sir, is endothermic, right? But bond enthalpy by nature is endothermic. And please understand that we can actually measure bond enthalpies. How can we do that? It's not a part of your course, but you can use a mass spectrometer to actually measure bond enthalpies, right? Now, a little recap from chapter number 4, which I've taught you. In chapter number 4, remember when we used to talk about the bonds between halogen atoms, the bonds between halogens, right? I bonded to I, right here. And when we were talking about these bonds between halogen atoms, we said, hey, which bond is the strongest? We said, hey, chlorine's bond is the strongest, right? And that's why you need a lot of energy to break this bond. The bond enthalpy for breaking chlorine molecules bond enthalpy to break this gaseous molecule is pretty high. Let's assume they're all in their gaseous state. Let's assume, right? They're all in their gaseous state. Let's assume for a moment. Just assuming. So to break this bond, you'd require a higher energy, right? And then to break this bond, relatively lower energy, and to break the I bond, the lowest energy. And we had already studied this because chlorine is smaller in size, it's smaller in size. And so what happens is that it has a shorter bond length. Bond length is shorter, a shorter bond forms because the shared pair of electrons and the nuclei are pretty close to each other because of the smaller size. So the bond length is shorter. I'm just recapping chapter 4. So the shorter the bond length, and therefore if the bond length is shorter, you need to provide it with a lot of energy. Therefore we also used to say what? We also used to say that the bond enthalpy, sir, is also pretty high for breaking the Cl-Cl bond, right? Because here, when you were to overcome the attractive forces, you would require a much higher bond enthalpy compared to this and this, because this is smaller in size, this is larger, the shared pair of electrons and the nuclei are further away from each other, so the nuclear attraction is relatively weaker and the bond length is longer. It's a longer bond. Longer bonds can break easily. You need, if you have a longer bond length, the bond enthalpy is going to be less, right? And so that's the conclusion which we arrived at even in chapter number 4, that we said, hey, the higher the bond enthalpy means what? The higher the bond enthalpy means stronger the bond. Stronger the bond. So if I say, why is chlorine's bond stronger? It's because it has a higher bond enthalpy and it's shorter. It has a shorter bond length. It's smaller in size. But if I say, hey, what if the bond length is higher? What if the bond length is longer? Not higher, but longer. What if the bond is longer in length? Then what? Then the bond enthalpy is less. You need less energy to break the bond, right? Don't you? And we've already studied this. Yeah? So that's the idea. And we've also studied the idea that if you have more electrons, and this we've studied in chapter number 4, if you have more electrons, you would have a higher bond enthalpy, because more electrons effectively mean what? More forces of attraction, more attractive forces, right? More electrons in a bond, to be more specific, more bonding electrons, because there are more interactions. Remember when I taught you guys Coulomb's law? Just a snippet of Coulomb's law to teach you guys this idea. But this is all about bond enthalpy and bond energy. Now, the question is, how is it connected with Hess? How is it connected with Hess's law? That's the actual question. And before we dive deep into that actual question, again, I want to recap a certain information from O-Level and IGCSE, which was, why in the hell would we ever need to know about bond enthalpies? Why do we need to know about bond enthalpies? Because these bond enthalpies effectively helped us calculate the enthalpy changes, wouldn't they? Remember the rote learning that you guys did? Bonds broken minus bond form equals the enthalpy change. Remember this fella? So these bond enthalpies, which were actually measurable for obviously gaseous molecules, you were using them to calculate the enthalpy changes. And I'll give you the most basic example, which you also studied in O-Levels and IGCSE, which is if you have methane and it burns in oxygen, two oxygens obviously, and it gives you carbon dioxide and water. Let's suppose all our gases, I'm going to assume all our gases. I'm just assuming that stuff, right? So if all our gases, remember, bond enthalpy works if all the molecules are in their gaseous form. Please, this is so important. See, it's defined as breaking 1 mole of a specific covalent bond of 1 mole of gaseous molecules. This is so important, and I'll tell you why in a moment. So it's always for gaseous molecules. That's why I'm assuming this. And in O-Levels, they used to assume this for you guys. Right? So how would we calculate the enthalpy changes through bond enthalpies or bond energy? How would we calculate it? Sir, the examiner would give us a very beautiful table. Remember this table of bond enthalpies? Let me show you guys that table. Give me a moment. Let me show you guys that table, which used to be given to you guys. This table right here. This is bond enthalpy. Right here. So we would actually use this to actually figure out the enthalpy change of the reaction. How? We'd say, hey, CH4 looks like this, carbon bonded to 4 hydrogens. Oxygen looks like this, O double bonded to O, right? And then you have carbon dioxide is bonded to 2 oxygens right here. And then you have water, which is bonded to O, bonded to 2 hydrogens, right? And you have 2 moles of that stuff. Now, the way we used to go about this was that, hey, new bonds cannot form. You can never, ever form new bonds if old bonds are not broken. Remember this. Carbon dioxide and H2O, they cannot form unless and until these bonds are broken. So old bonds must be broken for new bonds to form. and that'll hit you guys in the tummy after A levels, right? So old bombs, there's a reel on Instagram which says our chemistry teacher did not lie when he said old bonds must be broken for new bonds to form. So these old bonds, and snakes, stay away from me, snakes. So these old bonds must be broken, right? And we know that bond breaking is an endothermic process. So we're gonna break all of these bonds, right, using our bond enthalpies, and then we're gonna form all of these bonds, right? So, and then bonds broken minus bond form is going to be enthalpy change. And the reason for that is pretty simple, because why are we saying bonds broken minus bond form? Because bond formation is exothermic and we write a negative sign with it. So let's do this. Let's break the CH bond, the CH bond, the CH bond, the CH bond. We're breaking 4 CH bonds plus we are breaking how many O double bonded to O? 1 O double bonded to O, 1 OO bond, right? This is the energy that's going to be taken in during bond breaking. And what's the energy given out during bond formation? So we are forming CO bond here and another CO bond here. So we are forming 2 CO bonds. Done. And how many OH bonds are we forming? 1, 2. We are forming 2 OH bonds, but that's for 1 water. We have 2 water. So in total, we are forming 4 OH bonds, aren't we? So we have 4 OH bonds, right? Because see, 1 OH, 2 OH, it's like 2 waters are there. So if you don't understand this, you could say, hey, instead of writing a 2 here, you could say, hey, you have 2 waters. Look, you have 1 water here, 1 water here. So 1 mole of this would break, 1 mole of this would break, 1 here, 1 here. So 4 OH bonds, 4 OH bonds would form, right? So that's the idea. So last time I took your class was in June for Chem P1. I'm taking it after this. Good to be back. That's awesome, Anam. I'm glad. Hi, Anam. I'm glad. So, sir, I solved a difficult Hess cycle question in class today using your method, and our teacher was so surprised I was the only one to solve it. I'm glad. I'm glad, guys. Acha, can we stop flattering Sir Suleiman and focus on the question? Thank you. Acha. Let's move on. So what's the bond enthalpy? It's like simple, like even my grade 2 sister could do this, that it's a CH bond right here, and that's the bond enthalpy for it. So 4 into plus 413, that's it. And I wouldn't even write plus. 4 into 413 plus 2 into, what's the energy required to break the OO bond? It's 498. What's the overall energy taken in during bond breaking? Somebody help me out. It's what? It's 2640 kilojoules. Please understand, do not put any positive or negative sign here, because we are talking about energy. See, bond breaking, if it's bond breaking or bond formation, it's energy, and energy we all know from O levels and IGCSE, it's a scalar quantity, not a vector quantity. The only reason why we write the negative sign is to show that is the reaction exo or endo, and for that we use the term enthalpy changes. So whenever you talk about enthalpy changes, you have to write the positive or the negative sign with it. But when you talk about just energy, what's the energy taken in to break the bonds? That's 2640 kilojoules. That's it. No positives, no negatives. That's so important. And similarly here, 2 times CO bond. What's the CO bond? 805. See, I'm adding no signs whatsoever because it's energy. 4 times OH bond. OH bond is 464. Somebody calculate this stuff for me, please. What do you get? Yeah. 805. Huh? Can Sir, can you be the carb to my oxel? Yes, Anam, I'll post these recordings on YouTube. Said listen for catch up. 34660. I doubt that. 34660. No. It can't be this much. Let me use my calculator. It's like 34,000 pe pahunch gayi hain. 2 times 805 plus 4 times 464. That's 3466. I don't know where the extra zero came from, kiddo. So that's the energy given out during bond formation, isn't it? And so what's the enthalpy change? Enthalpy change is bonds broken minus bonds formed. And so what does that give me? It's 2640. See, here I'm putting the negative sign, because in enthalpy change, I have to tell the examiner, right? So it's minus what? 2640 minus 23466. what does that give me? Minus 826 kilojoule per mole, right? And this is how enthalpy, bond enthalpies actually helped us calculate the enthalpy changes, right? And we've seen the practical version of this as well. In O levels, you've seen this, that in order for any reaction to take place, you must first break all the bonds of the gaseous molecules to convert all of them into gaseous atoms, and then bonds must be formed, right? And I'll show you a picture for it. A very beautiful picture. Where is it? Where is that beauty? Let me show you guys a picture. And that's important to visualize this. Yeah, keep on visualizing this. Here you go. See? Oh, this is for H2O, but it's the same idea. It's for H2O, but the idea is the same. See? Hydrogen reacting with oxygen to give you H2O. So what happens is they're all in their gaseous state, right? So first what happens is energy is taken in to break all the bonds, and you end up with gaseous atoms. You end up with gaseous atoms right here. And then energy is given out to form bonds. Right? So effectively, even if I talk about CH4 reacting with oxygen, 2 moles of oxygen, right? What's going to first happen is all the bonds are going to break. And you're going to end up with gaseous atoms. You're going to have gaseous atoms right here. Right? And then all the bonds are going to form, and you're going to end up with products right here, which is what? Carbon dioxide and H2O. And you have 2 H2Os, right? So that's the idea. Energy must be first taken in to break all the bonds of these gaseous molecules to get gaseous atoms. You're going to have C gas here. You're going to have H gas here. 4 H gases. You're going to have, 4 O gases. Why 4? Because see, when you break one O2 bond, you get 2 oxygens, and you have 2 of this. So you're going to have gaseous atoms all over here. And then they're going to form bonds, right? So that's the idea. And so this is my enthalpy change. See? Right here. It's exothermic. It's negative. Why? Because this is the energy taken in during bond breaking. This is the energy given out during bond formation. And energy taken in during bond breaking is less than the energy given out during bond formation. Right? That's the idea. Yeah? So this is how we used to calculate it back in the day. But in A level says, hey, I have not taught you Hess cycle. I've taught you. It's not taught it, guys. It's taught. So I've taught you guys Hess cycle now, and use the same idea, which is CH4 plus O2 gives you carbon dioxide and water, and 2 moles of these water, and they're all gaseous. Please assume that they're all in their gaseous state. All are in their gas, because bond enthalpies only work for gaseous states, right? So Hess cycle said, hey, this is basically a copycat. You are trying to copy me. This is basically derived from Hess's law or Hess cycle. Sir, how is this derived from Hess's law or Hess's cycle? Let me tell you. If you want to figure out the enthalpy change right here, this is what we did, right? And you're given bond enthalpies. Which is all the way here. Let me add the picture again for bond enthalpies. Let me add the picture. Hold up. Hold your horses. Young fella. Hold your horses. Right? So if you're given bond enthalpies, one way to calculate is to use this idea, which is the formula. Right? And the other way to calculate the enthalpy change of reaction is to use the Hess's cycle. And how do you do this? You say, hey, I need to break all the bonds. You just break all bonds. Whatever you have, just break them. And when you break all bonds, you're going to end up with what? You're going to end up with gaseous atoms. Isn't this what happens? You break all the bonds and you end up with gaseous atoms. So Hess cycle says, hey, just start breaking all the bonds. Even for products, break all the bonds. Because bond enthalpy is defined in an endothermic manner. So I'm going to break bond to get gaseous atoms. I'm just going to break all the bonds. Let's break them. So I'm going to break 4 CH bonds right here. 4 times 413. Right? I'm going to break 2 O2 bonds, which is right here, 498. I'm going to break carbon dioxide bond, which is 2 C double bonded to O, which is 805 right here. And then I'm going to break H2O bond. So which is 4 times OH, right? 4 times, what's OH right here? 464. And Hess said, hey, they've just copied. Why? Because the indirect root equals the direct root. So you guys can now calculate this. See, it's 4 times 413 plus 2 times 498. This is the energy taken in to break the bonds of these reactants, right? And then this would be equal to the enthalpy change of the reaction plus 2 times 805 plus 4 times 464. Can somebody calculate this for me, please? What do you get here? And what do you get here? Somebody calculate this. So you get 2648 here according to a student. And what do you get here? Plus, what do we get here? Shabash. This is where connections start to come into play. 43466. So what's the enthalpy change of reaction? It should be the same as minus 2 minus 8. See, this is 2648 minus 3466. And what does that give me? That gives me the same answer, which is effectively minus 826. Now, there might be a couple of questions which I need to address right now. See, the answer is absolutely the same. The answer is absolutely the same. And this is how the formula was derived. See, bonds broken, this is the energy taken in during bonds broken. Bonds broken minus bonds formed. See, bonds broken minus bonds formed. This is how the formula was actually developed, right? Now, there's a question. Is it 818 or 826? You guys have done the calculations. I can't use the calculator for you guys. Sir, you explained so well. Great job. Thanks, Aisha. Acha. Now, there are a couple of things which you need to understand. The first question, which a lot of students might think right now is, sir, I got it. You just broke all the bonds. You just broke all the bonds and you figured out the enthalpy change through Hess's cycle, and we used to do it through the formula as well. So can we do it through both methods? The answer is yes. You can do it through both methods, right? The next question that students ask me a lot of the time is that, sir, don't try to be sneaky with us. Don't try to be sneaky with us. What do you mean? What do you mean? I'm not being sneaky. What? Sir, you just literally told us to break all the bonds, didn't you? You broke these bonds, you broke these bonds, you broke the bonds of products. But sir, we don't break the bonds of products. We form the bonds of products, right? And you guys are right. We do it. We don't break the bonds of products. We form them. So sir, shouldn't your arrows look something like this? And so this is something very conceptual. And I know nobody asked this question. I just made it up. That because I used to think like this, and I want to make sure that no kid has any confusion in their entire existence with this stuff, right? I don't want to just teach you guys rote learning that, make all the atoms, make all the arrows to gaseous atoms and break all the bonds. No, because a person may ask you, hey, okay, I understand you want to break these bonds, you want to break these bonds, but why are you breaking these bonds? Shouldn't the gaseous atoms form these bonds? Isn't that true? Shouldn't the gaseous atoms form these bonds? Isn't this what happens? You break the bonds and then gaseous atoms form the bonds, don't they? Who's going to answer this? Why have I not done it like this? And could I do it like this? And if so, what would I have to change? Sir, it's minus 818. Yeah, you guys are using the calculator. I couldn't care less if it's minus 826 or minus 818. Couldn't care less. I swear to God. Somebody saying 818, somebody saying 826, whatever it is, to hell with it. I'm here to teach you guys the method. Please understand the method rather than 816 and 8. Do you upload these meetings onto YouTube? Yes, Yumna. I upload some of them. This is the last meeting will be uploaded onto YouTube, and then it's it. Then we're starting off the next chapter with my live class. But hey, somebody please. Hasib, you beauty. Hasib, you beauty. Love it, man. Love it. And Raima, beauty. So both answers are very well valid. And let me tell you what both of them said. Hasib said that, sir, if you were to go from gaseous atoms into these products right here, then, sir, you would form bond. And bond formation is exothermic. Then you would not say 2 into 805. Then you would say 2 into minus 805. Right? And then here you would say 4 into minus 464. And you'd get your same answer. You could calculate it, you would get the same answer, right? Because then what would happen is that this would be the indirect route and this would be the direct route, right? And I could write it here. 4 times 413. That's what Hasib said. And this is what? 2 times what? 498. This is what Hasib said. You guys can calculate it. You would get the same answer. If it's 818, for crying out loud, I wanna jump off the roof. I wanna kill myself. I don't know what to do. I'm having a tantrum. No, I'm joking. Beta, chullu par pani lena. Khatam. Pani na le. Usme zahar dale. H2SO4 dale. Yeah? That sounds fun, right? It doesn't it? Because I've said a billion times, if it's 818 or 826, kill me, please kill me. I'll give you my address, come here, kill me. How many more times do I have to say? Sorry. But hey, okay, coming back to this. So Hasib said you would put a negative sign here because if bond formation is taking place, then you'd put a negative sign. But Raima explained it in a very beautiful manner. Raima said, sir, I'll also tell you why you have to put the negative sign. Hasib said it's bond formation and bond formation is exothermic and therefore you'll have to put a negative sign here, a negative sign here, right? That's what Hasib said. But Raima gave me a cherry on top. Raima said, sir, bond enthalpies are given from the perspective of an endothermic process. They're given from the perspective of an endothermic process. They're given from the perspective of breaking a bond, not making a bond. Right? Although if you break a bond and then you make the same bond, right? The energy taken in to break the bond would be the same as the energy given out to form the bond, right? If I were to break the CC bond, it would require 347 kilojoules of energy per mole. And if I were to form it, it would still give off 347, but it's defined from the perspective of an endothermic process. That's the reason why when I was pointing from the products to these gaseous atoms, I did not put any negative sign here because if I'm breaking them, it's endo, it's endo, it's endo, it's endo. So that's a shortcut to it, but if you want to use your logic could look something like this. But remember, if you're using your logic, make sure to then put a negative sign here because these bond enthalpies are given from the perspective of breaking bonds, not forming bonds. So if you were to break the bond, then it would be 805, but if you're forming bond, then you'll have to put a negative sign to it, and I rest my case. And I'm pretty sure a lot of you might have been confused when your teachers would have taught you this idea that, hey, just make gaseous atoms and break all the bonds, right? And you might be wondering, hey, up until now, we break the bonds here and then we form the bonds. Why are we doing this? So you could do the other way as well, but then make sure to put the negative sign, right? I hope you guys have your conceptual clarity. Sir, what's your address for me to kill you? Everybody's right? Now, let's do one example and then we'll move on to some more details, right? And that example I'll give you, you guys do it on your own. Hydrogen plus Cl2 gives me 2HCl. What's the enthalpy change if the bond energies of HH is like 435 kilojoule per mole and Cl is about, if I remember, I'm not wrong, Cl is 240. No, balki nahi, main hi nahi de raha. I'm not giving you guys Cl. Wait, I'm not gonna. I wanna shake this up a little. HCl is about 431, and this enthalpy change right here of the reaction is minus 184. Calculate the Cl bond enthalpy. And fun fact, this idea is used to calculate bond enthalpies even. It's the most useful for estimating bond enthalpies. Please calculate the bond enthalpy of Cl bonded to Cl. Use the idea which I've taught you. You could use the logical way, but in exams we are short on time, so we need to just quickly khalas things, right? So finish it off. We use our 3-box diagram the same way. I'll add it right here. Again, I'll add it. You had H2, you had Cl2, and this is given to me, which is what, minus 184. This is 2HCl, right? And just gaseous atoms all over. So the moment I see bond enthalpies, and you could have also calculated it in the other manner. It's up to you, however you want to calculate. From the formula, which you've learned, enthalpy change equals bonds broken minus bonds formed. You could learn it like this, but I don't recommend this because later on during this class, you'll see why I don't recommend this anymore, because things get a little complicated, right? So let's just break all these bonds. To break the Cl-Cl bond, the bond enthalpy, I don't know. To break the H-H bond, I know it. I know the bond enthalpy. What is that? That is, it's given to me plus 435. That's 435, right? And to break the HCl bond, how much bond enthalpy do I need? 431. And since that's for one HCl, you have two of them, so I'll multiply this by 2. Right? So what do you get? The indirect root equals the direct root. Done. So 435 plus x equals minus 184 plus 2 times 431. What is x, guys? What is x? If you're done with your x, I'm moving to the next. Astaghfirullah Rabbi min kulli dhanbin. Yes, sir. What do you get? This is plus what? 862. And then minus 435. What do you get? X equals? X equals, sir? Anybody? 243? 243 kilojoule per mole. See, that's how you could even find out the bond enthalpy. See, this is the bond enthalpy for Cl bonded to Cl. Right? And you could have also used the formula. So if you want me to use the formula, it's also like this. See, enthalpy change equals bonds broken minus bonds formed. What's the energy taken in to break the bond? To break the HH bond, it's 435 plus, to break the Cl bond, I don't know. So 435 plus X, right? And then minus bond, or for now, I don't even want to write this. I'll tell you why. So what's the enthalpy change? It's minus 184. Bonds broken, I want to figure out. Bond formation is given to me, which is what? 2 times 431. 2 times 431. So can somebody calculate the energy taken in during bond breaking? Shift this there. What do you get? 862 minus 184. What's the energy taken in during bond breaking? The overall energy taken in during bond breaking. What's that? 678. Right? That's the energy taken in during bond breaking. And this comprises of two things. One, what? The HH bond, which is 435, if I'm not wrong. And then Cl bonds broken, which is X. I don't know that. And overall is 678. So this goes there. X equals 678 minus 435. And you'll get the same answer. If you guys have calculated the previous one correctly, you will get the same answer. Done? Yeah. So you guys can absorb this for a moment. Give it one moment and try to absorb this before we move on. Right. Before we move on, try to absorb this. If you're done, sir, please sing. Lela kamiste turma bachurke halun dre chalur ma bachurke. More at the end. Bas. Oh nahi. ठीक है यार, ये तो अभी भी रहता है. आई एम टायर्ड एंड चलो बाकी कल कर लेंगे, कल ख़त्म करते हैं इसको. जस्ट लेट मी जस्ट टीच यू गाइज वन शॉर्ट कॉन्सेप्ट बिफोर वी फिनिश दिस टुमारो. टुडे आई वांट टू टेक अ शॉर्ट क्लास. Sir, can you stay here a little? I want to write it. Sure, Faryal. Okay, the last concept which I want to teach you guys is extra stuff, not related, but it's good to know it, right? And the idea goes something like this, that this value that you've calculated, this theoretical value, is actually incorrect. Both these theoretical value are slightly incorrect. You know, maybe not for them, but normally these theoretical values that you guys calculate are slightly incorrect. And the reason for that is they're slightly different. We don't say they're incorrect, but slightly different than the actual value. And one of the most important reasons for that is that, number one, we assume that everything is in its gaseous state, right? We assume everything is in its gaseous state, even though, you know, some alkenes may be liquids, so H2O may be liquid. We assume that everything is in its gaseous state, right? That's the first thing. But the most important reason for that is because we take average bond enthalpies. And you'll see the word average bond enthalpies written in your exams as well. And so when you see it, don't get confused. Average bond enthalpies is basically this table. This table is average bond enthalpies. It's not the actual bond enthalpy of the CC bond. No, it's an average bond enthalpy. Sir, what in the hell do you mean by average bond enthalpy? What do you mean by average bond enthalpy? See, The reason why I'm saying it's average bond enthalpy is because the energy required to break a specific bond, the energy required to break a specific bond right here, it varies slightly depending on the molecule it is in. Right? I'll repeat. The energy required to break this bond right here varies slightly from molecule to molecule. It depends in which molecule are you breaking the CC bond. Right? Similarly, any other bond, for example, the OH bond, if you were to break this OH bonds, this OH bond is different for water and different for alcohol. We know alcohols also have OH bond. So these bond enthalpies to break this bond in alcohol would have a slightly different value than to break this bond in water. To break the OH bond in water will be slightly different to compared to breaking the OH bond in the alcohol, right? And this is so beautiful. And so it isn't practical. It isn't practical for us to have a unique value for every single bond in every single molecule. It's going to kill us. It's going to waste our time. Think about it. If I start to look at this OH bond and I start to give you a molecule and I have billions and billions of molecules on the face of planet Earth. So should I start going around breaking every single molecule which has the OH bond and breaking it and seeing what value do I get, what value do I get here, what value do I get here, what? It's gonna waste a hell lot of time. Humans cannot do it practically. It's impossible to practically do it. It'll waste it'll waste a lot of time. Maybe hundreds of years, because there are billions and billions of molecules containing the OH atoms, right? The OH group of atoms. So kin ka todenge, right? And that is the reason why we use a single average. That is the reason why we use an average. Now, how is this average calculated? Again, not a part of your course, but the way you calculate this average bond enthalpy is that you break this bond, you break the OH bond across a wide range of different compounds. So we start breaking the OH bond across a wide range of different compounds, right? And when you start breaking the OH bond across a wide range of different compounds, you get different bond enthalpies. And when you get different bond enthalpies, you just take the average of that. And that's how you end up with the values that have been given to you in the exam. Please understand that these are mostly average values because it's practically impossible to calculate the CC bond for every single molecule, the bond enthalpy for C bonded to C for every single molecule individually. It's impossible. So what we do is we just take a wide range of compounds, wide range of different compounds and break this CC bond, break this C double bonded to C in those compounds and just take the average of that, right? Just simple average. And that's how we end up with average bond enthalpies, right? And let me just show you the one final picture and you're good to go. Then you guys can take the off day. And these things, these concepts, you'll see yourself standing out in the A-level exam even. When you read the question, you will know what the question means, right? See, this is a bond. A bond enthalpy is the energy change required to break and separate 1 mole of bonds. My definition is better. But this is also how they define it. But I was talking about average. I was talking about the average stuff. And I'll show you guys this. Where is the average term written? Where is that picture? I think I found it in one book. I remember back in the day. I remember a book. A book. Let me show you guys that stuff. You know, we're near the end of our chapter. Here we go. I found it. Just give this a read. See? The bond enthalpy of a particular bond is the energy required to break 1 mole of covalent bonds in 1 mole of gaseous molecules, right? And again, my definition is better. So yeah, it can also be defined like this, but mine is better. See, the mean bond enthalpy or the average bond enthalpy. And this is, by the way, Pearson and Excel's book, right? This I think is AQA or IB book, but this is Pearson and Excel book. So all the Excel students, listen to this. See, the mean bond enthalpy of XY bond is the mean value of the bond enthalpy values for the XY bond averaged across a wide range of compounds. See, so you're basically taking the mean value, which is effectively the average, right, of the XY bond. How? By averaging it across a wide range of compounds. See, they've also defined it like I have. So this is one idea, and that's why when you read the Cambridge questions, the Pearson and Excel questions, they will never say the bond enthalpy is this much. They will normally use the word what? The average bond enthalpy. And these things help you out in interviews as well, because now you say, okay, Cambridge, I know why you are saying average bond enthalpy. So you need to understand the questions before answering it as well. ये मेरा दावा है, आप you ask your friends if they know what this question means when they say the average bond enthalpy. They'll just say they've taken the average. Why not give you the actual? They'll come up with their own ideology. I don't know.